Good morning, everyone. Welcome to this morning's press conference on what's happening to the Sunspot cycle. We're here at the 224th AAS meeting in Boston, Massachusetts. I'm Rick Fienberg, AAS press officer, and I just want to make a quick announcement to the attending press. If you're planning to go to the press dinner tonight, there are directions on the table next to the mailboxes in the press office. It's really easy, though. You basically just take the green line from Copley to Science Park. And a bunch of us will be leaving around 6 o'clock from the hotel lobby. So just, bring your badge in case we need it to get into the planetarium, since it'll be after hours, I think. We'll go. We'll go to dinner and we'll go to the planetarium, but not in that order. All right. As I think you know, this is a joint meeting of the American Astronomical Society and 3 of its divisions. We have 6 topical divisions. The Historical Astronomy Division is here with us. The Laboratory Astrophysics Division, our newest division, is here with us. And one of our 3 biggest divisions, the Solar Physics Division, is here with us. And the 3 biggest divisions have their own press officers. They're volunteers, they're scientists themselves working in those fields. And we're privileged to have the press officer from the Solar Physics Division here with us today. That's Craig DeForest from the Southwest Research Institute. And I'm going to turn the podium over to him to introduce today's topic and speakers, since he helped put this thing together. Craig?
Is that me? Sorry. That's my kids. They just got up. We're here to talk about the 11-year sunspot cycle, which is maybe the most famous of all solar phenomena after sunlight. It's an about roughly 11-year cycle of magnetic activity that's been known, for hundreds of years. It's reflected by motions in the deep interior of the star. It's thought to affect climate, and it does drive space weather, which is a topic of big importance for a spacefaring society. We are in the solar maximum activity phase right now, but as most of you know, it's a very weak solar maximum. And over the past few years, we've had speculation that the sunspot cycle might even be shutting down for a while. Now, we have an update on the status of the solar cycle from 4 distinguished experts. We have Dr. Rick Bogart from Stanford University, who will talk to us about the solar interior and the motions in the interior of the star that are driving the current strange sunspot cycle. We have Dr. Dick Altrock from the Air Force Research Laboratory, who's been studying the effect of the solar cycle on the corona for many years, and has some insights to share on how the corona is responding to the strange cycle. We have Dr. Dave Webb from Boston College here in town, who has some new insights on the relationship between magnetic activity on the sun and solar storms, coronal mass ejections, and how that has changed in the current cycle. And finally, we have Professor Sarbani Basu from Yale University, who will sum up the results and discuss how this cycle fits into the context of what we know about the cycle in general. So as always, we'll go through the speakers one at a time. Each will hand off to the next, and we'll take questions at the very end. Thanks. So, Rick.
Thank you, Craig. So, yep. Okay. So, as Craig explained, the sunspot cycle is a quasi-periodicity in the appearance of magnetic activity and strong magnetic activity, as evidenced by sunspots. But it's also been known, and that's been known for hundreds of years, well, actually about 150 years. Also in about 1980, people made an interesting discovery that this cycle was also related to a completely different phenomenon. There certainly must be related, but that had to do with motions at the surface and beneath the surface of the sun. The sun rotates differentially, meaning that at the equator it rotates faster than at the poles. It's not a solid body, so there's no reason that it has to rotate at the same rate. And in fact, it rotates substantially slower at the poles. And that has also been known for about 150 years. Actually, no, it's been known for 400 years since the sunspots were discovered, because people measured the motions of the sunspots and could see that the ones at lower latitudes moved faster than the ones at the higher latitudes. And actually, I guess you could say that the solar activity cycle, the magnetic activity cycle, the reason that there's magnetic activity in sunspots, and the differential rotation are the two big, grand problems of solar physics that we aim to understand, and they've been there since Galileo discovered them 400 years ago. But around 1980, people were making very careful measurements of the differential rotation, and they discovered that there were actually very slight variations in the east-west motions, the westerly motion, which is the same as the rotation rate, that varied in time. And they gave to this phenomenon, they called it the torsional oscillation. And here's this first slide tried to illustrate that. What is shown here on the slide, the axis, the x-axis, is time. So this is going from like about 1995, the beginning of the gong measurements of helioseismology, so we can make subsurface measurements, up to the present, to 2014. So that, and the vertical axis is latitude on the sun, and what's plotted at each point is the difference between the local rotation rate, the east-west motion at that point in time and at that latitude, and the mean over many, many years. And what you can see is that there are these jets of approximately a few meters per second, and that's not a very fast motion. A meter per second is like about 2 miles an hour, so this is like a very, very gentle breeze that you wouldn't even be able to feel if you were on the sun. But nonetheless, we can measure this, and we see that these jets propagate, they move from high latitudes to low latitudes, and it turns out that the sunspots actually occur at the edges of these jets, and there's also another jet that goes towards the pole, and there's a kind of a constant phasing between the two. As far as we know, we've only really been able to observe this phenomenon for about 3 solar cycles since it was discovered. And this also led to the idea that there was actually an extended solar cycle, because although the solar cycle itself is 11 years, very roughly, the sunspots come and go with an 11-year periodicity. You can see, just by looking at this map, that these features last much longer than 11 years. It's actually about 17 years from the time that these jets occur at high latitudes to the time that they manage to propagate down towards the equator. So, so this has been a subject of great interest. And we've been exploring this with helioseismology, which allows us to probe the motions below the surface of the sun, the visible surface. So since 1995, we've been doing that. And these results are actually based on global helioseismology. So these are down to a depth of about 9,000 kilometers below the surface, 7,000 kilometers, excuse me. There's one key problem with the global helioseismology. You'll see that this looks very symmetric, north and south, exactly the same, northern hemisphere, southern hemisphere. It actually is precisely symmetric, and that is because global helioseismology, although it can distinguish effects at different latitudes, cannot distinguish the north latitude from the same latitude in the south. So these are actually, this is somewhat of a fake. It's really just a mirror image. The signal we see is the average signal at 40 degrees, for example, from 40 degrees north and 40 degrees south. So they'll be exactly the same. However, with the advent of very high-resolution images from space with the Solar Dynamics Observatory and the helioseismic and magnetic imager that I work on at Stanford, we have actually been able to use a different technique of local helioseismology to actually measure the flows at particular locations in latitude and longitude. So there's none of this symmetry and none of this averaging in longitude and averaging north and south. And these are the results that we're starting to see. And this is for the first 3 rotations that we observed. The sun rotates in a period of about 27 days, seen from the Earth. And for each rotation here, I've shown, these are just maps of the sun, latitude in the vertical direction and longitude in the horizontal direction. From 0 to 360 degrees, there's a rather arbitrary coordinate system that has been defined. It was defined by Richard Carrington back in 1863. He took the average of the sunspot motions and said, well, they seem to, on the average, they seem to rotate at a rate of 25.38 days, so we'll just define a coordinate system. We'll say this is the 0 of longitude, just like the Greenwich meridian, and we'll say every 25.38 days relative to the stars, it comes around again. So at every 27.25 days from the Earth, it comes around again. So you can see the dates when that 0 longitude occurs from one rotation to the next. The interesting feature here is the jet at rather high latitudes, and it's a northern hemisphere effect. It's sort of north of 45 degrees. And you see it's a kind of an east-west or actually northwest-southeast kind of jet of a negative flow. The blue means a negative flow, red is positive, which means it's somewhat slower than the rotation, the average rotation at that latitude. In this case, again, the scale is saturates at 0.5 meter a second, which is like 1 mile an hour. So that's like practically a crawl. Nonetheless, it's quite clearly seen over and above the signals at low latitudes, where you see these blotches, which are actually much stronger flows associated with the sunspots themselves. There's convergent flows towards the sunspots, but those are very localized. These jets are very interesting, and we see them with other techniques of helioseismology as well. There's a different technique called time distance, in which we measure the travel times from point to point of a wave at the surface. I want to highlight this because that technique was pioneered by Tom Duvall, who was yesterday's winner of the Solar Physics Division Hale Prize. So this is using his technique. The bottom row, the top row is the local helioseismology ring diagram technique that I've used. And I've actually overlaid the 2 results in the center, and you can see that they agree very, very well, which is nice because they probe somewhat different depths, but it means that it's fairly consistent with depth. Another interesting measurement was made, reported in Science magazine last December. David Hathaway and his collaborators were measuring the motions of supergranules, which are a flow field at the surface visible at the surface of the sun. So this is not helioseismology, but they also saw these same structures, and you can see in the bottom. But there's a very interesting story about this, because as you can see, the structures look very similar, in particular that jet in the northern hemisphere, but they don't align. They're in a different location. And I thought, well, that's rather puzzling. Why is that? Well, I saw Dave Hathaway yesterday at the meeting, and I asked him about this. Well, why? This is very curious. And he said, well, how much are they offset? And I said, well, that's just roughly 90 degrees in longitude. It's quite a lot. It's not a small effect. He said, oh, I know what. I moved the longitude center of my maps by 90 degrees to put the interesting feature in the center. So in our maps, 180 degrees, it's like Hawaii is in the center, but he said, oh, I can see the Great Wall of China, so I'm going to put China in the middle of these maps. So, so they actually do agree precisely when you align them in longitude correctly. So now the subject of this is, of course, the evolution of these flows. And you can see, I've just got a little movie here where I go from one rotation to the next. And we've been observing for 4 years now with HMI, so that's 54 rotations. And you can see that these jets kind of come and go. They were stronger towards the beginning of the mission, which was near the peak of the solar activity. They seem to last for about 3 to 4 rotations, and then go away. Sometimes they appear in the south, sometimes they appear in the north, sometimes they appear in both. Sometimes they're faster, sometimes they're slower. So the features that we saw on the original torsional oscillation map are just very long-term averages of things which are actually coming and going with a much higher frequency and in space and time. So there's much more complexity to this than we originally realized with the simple torsional oscillation pattern. So you can see that averaging is wiping out just a lot of fine structure. Let me, for the final slide, let me just show the same feature as seen in our local helioseismology, that's where I've just taken now the latitude averages and made a movie in time. So you can actually see that same torsional oscillation pattern of the things moving towards the equator, the jets moving towards the equator. You can see now in the flows, you can see that as time progresses, that jet of red moves towards the equator and eventually converges. And at the same time, you can see that there's a jet moving towards the pole in the northern hemisphere, near the high latitudes, but it's not happening in the southern hemisphere. Now that may explain that particular strange feature, that where is the poleward flow? Where's the poleward jet in this current cycle? We're not seeing it. Well, it looks like we're seeing it in one hemisphere only, so it's a much weaker signal. We're not seeing it in the south. The other interesting feature that I just want to call attention to is the meridional flow, the north-south flows. There's a mean circulation from equator to pole in both hemispheres, which is carrying magnetic field from the sunspots towards the pole. We think that that's how we're pretty sure that's how the solar cycle is organized. But superimposed on that, we've also shown, we're able to measure the anomalies, and we can see, if I can get this centered here. Why is this not working? There we go. You can see that they're, instead of a hemispheric difference, they're the same. It goes kind of like from red at the beginning of the 4-year period to all blue towards the end of the period, which means that the first 2 years of the mission, we had somewhat northward motions relative to the mean flow all over the sun. And in the second half of that period, we had somewhat southward motions all over the sun, meaning that this meridional cycle, this meridional circulation, which is poleward in both hemispheres, was strengthening over the first 4 years of this cycle in the northern hemisphere. At the same time, it's been weakening in the southern hemisphere. Now, that may be related to the fact that we see this poleward jet in the northern hemisphere, but we don't see that in the southern hemisphere. So that's that's the latest status from our flow measurements beneath the surface. So I'll go now to the next speaker.
Good morning. So what I'm going to be talking about today are measurements of the temperature of the solar corona as a function of time. Now, everybody probably knows that the corona is the outer atmosphere of the sun. Which has been observed at eclipses for a long time, but maybe everyone doesn't know that the temperature of this outer atmosphere of the sun is above 1 million degrees. At our location in Sunspot, New Mexico, we have an instrument that produces an artificial eclipse of the sun on any given day that we were able to observe. And we observed the corona in two spectral emission lines that are formed in the corona. And this just shows two, excuse me. There we go. On the left side shows a picture of the corona on the 27th of May of this year in the light of an emission line that is formed at about 1 million degrees. And on the right is the same day showing a picture of the corona as formed in a line that's formed at about 2 million degrees. We've been taking these observations since 1983, so we have about 30 years worth now. And the two lines that are used to observe the corona are a line that's called iron 14, which just means 13 times ionized iron. You can imagine the temperature it takes to ionize that. It's about 2 million degrees. And also iron 10, which is 9 times ionized iron, which only takes about 1 million degrees to be ionized. Now, sorry about all the words here, but we can use these observations. It's been shown by calculations that if we take the ratio of the emissions in these two lines, that we can obtain the coronal temperature from that, which I'm calling TC. And you'll see that throughout most of these slides. So I'm going to take these observations and look at them over a period of about 30 years. Two caveats. One is that we don't try to look below 30 degrees, which is where solar active regions occur, because the method requires that the temperature along the line of sight through the corona has to be the same at every point along the line of sight. In solar active regions, that's not the case. So we only plot the observations at latitudes greater than 30 degrees. We also take temporal averages to lower the noise. And one thing that's happened recently is in 2014, there's been a tremendous outbreak of activity in the in the southern hemisphere of the sun. And the observations that I have only go through the end of 2013. So there may be things going on in 2014 that are going to change the results of this study, but we're following them, and we'll let you know. Well, here's the big picture. So what we have here is, I can find it, there we go. So we're plotting as a function of latitude from the North Pole to the South Pole. It's there someplace. Yeah, and from 1983 up through 2013, the temperature of the corona. Now, on this plot, darker is higher temperatures, lighter, lower temperatures. And one thing to notice is that for the last two solar cycles, these are the previous solar cycles. This is cycle 23, this is cycle 22, and we just got the very end of cycle 21 over there. Near solar minimum there is a tremendous temperature gradient between the lower latitudes and the higher latitudes, and that's shown by the fact that these contour lines of temperature are very close together. And that has been a feature of the solar cycle for the last two minimum. And then at solar maximum, the temperature gets much higher at the higher latitudes, and it also gets higher at lower latitudes. This is really difficult trying to find the cursor. So this is the southern hemisphere, this is the northern hemisphere. And in the previous two solar cycles, it's looked very similar with high temperatures all the way through the sun from 30 degrees latitude up to the poles. Now, what happens after the last solar maximum? Well, here we come to the minimum of between the solar cycles 23 and 24. And you can see that things look very different here. They're much different than they did in the previous two solar cycles that have quite a bit of similarity to them. Here, there's very little temperature change between 30 degrees and the pole, and the same in the southern hemisphere. So the hemispheric patterns that we see are one is sort of a check on the other to make sure that things are behaving the same across the sun. So that's one thing that's very unusual. The second thing is, if you look at the northern hemisphere, it's pretty certain that we did have a maximum in temperature in the northern hemisphere in about 2010, because now the temperature in the northern hemisphere is starting to go down and looking much like the temperatures in the solar minimum have looked in previous cycles. In the southern hemisphere, there was an early maximum of the temperature in about 2012, but we don't know what's going on since the end of 2013. So it's possible there may be another maximum of temperature off to the right of this plot that's not shown here. But there's no doubt that the minimum between the two solar cycles and also the maximum of this solar cycle are behaving extremely differently than previous cycles. Well, I'm sorry that this is not a very easy plot to follow, but what this shows here is a temperature plotted over here from 1 million, sorry. It was from 1 million up to 2 million degrees. I'm not used to this, maybe okay. And the solid line is the temperature above 30 degrees, averaged above 30 degrees latitude. And the dashed line is the temperature above 78 degrees latitude. So it's basically the polar temperature. And you can see in the previous two solar cycles, the behavior at 30 degrees looked very, very similar in the solar cycles that we had prior to that. And also the temperature at 78 degrees, above 78 degrees latitude, that is near the poles, looked similar in those two solar cycles. When we get to solar cycle 24, over on the right-hand side of the figure, we see that things have changed radically. The temperature at latitudes greater than 78 degrees, that is near the poles of the sun, has not gotten anywhere near as cool as it did in the previous two solar cycles. The temperature averaged over all of the sun that we can calculate did get down to a value that was similar, but the two temperatures greater than 30 degrees and greater than 78 degrees are similar, which they have not been in previous solar cycles. Now let's start going into the maximum. The asterisks show the sunspot number, and so on the right-hand side of the figure, you can see these asterisks going through a small maximum at about 2012. That was the maximum in the northern hemisphere of the sun, and then coming down to more or less a plateau up until now. But the maximum temperature that was attained is significantly lower than the maximum temperatures that were obtained in the previous solar cycles. So prior to this last solar minimum, there was a very well-defined solar cycle variation that varied by about half of a million degrees Kelvin near the poles. And the coronal temperatures for the previous cycles were very similar. That is, from one cycle to the next, they were quite similar. Since that time, that pattern has been broken. The temperature at the solar minimum increased significantly relative to previous cycles. But the major things that I want to end on is that the coronal temperature since the minimum reached maximum earlier in the north than in the south. And I think that's a definite statement. The temperature at the maximum of cycle 24 so far is significantly lower than in previous cycles. So what this says about the long-term variation of the corona, it's not really clear, but there's a definite indication that this solar cycle has been weaker than the previous two solar cycles. So that's all I have, and I'll turn it over to the next speaker.
Okay, I'm talking about comparison of coronal mass ejections, which we're calling CMEs here. This is a major part of solar activity you see over the solar cycle with sunspot number. Sunspot numbers, of course, we've been talking about, and everybody knows what sunspots are. I don't have much time, so what I'm concerned with and showing here at the meeting are various we've been trying to plot these, tracking the CMEs versus sunspot number over several solar cycles now. Really ever since the space age, we haven't really observed CMEs until the space age. They weren't easily observed in the corona. Now we can observe them over almost 4 solar cycles. So this is an update on plotting CMEs versus sunspot number over at least the last couple solar cycles, which is what we're focused on here. Now, coronal mass ejections are very large volumes of material, ejected plasma from the sun, and also magnetic fields into the heliosphere. They're important scientifically and from a society point of view. Scientifically, they're important because they inject large amounts of mass and magnetic fields into the heliosphere, and they may be one of the primary ways that the sun sheds its magnetic flux during the solar cycle, in fact. At least that flux that's in the corona. This shows an example of a CME. I won't go into details. This is with the LASCO coronagraph, which is on the SOHO observatory, which is at the L1 point in front of the Earth, and it's been there since 1995 or 6. And this is a plot of the CME rate from the counting from the LASCO coronagraph from 1996 until now, pretty much through towards the end of 2013, over on this side. This looks a little bit complicated, but the point is now we have, since LASCO was launched, we have several ways of identifying and counting CMEs, which has led to a little bit of confusion. The problem is people have used one of these, especially automatic counting techniques, to point out that the CME rate seems to be diverging from the sunspot number rate. In prior cycles with different instruments, we pretty much came to the conclusion that the CME rate tracked the sunspot number rate very well with a very high correlation. Now, since LASCO, and especially with more recent data from stereo, of course, things are more complicated, and we have to be very careful before making such statements like this. For instance, here in this plot, the sunspot number is shown in blue. It's relatively, the amplitude is subjective, so it's not a fixed amplitude with respect to the CME rate, which is shown on the left side in terms of CMEs per day. The sunspot number is on the right side. But you'll see in this relative plot that there are three ways of measuring the CME rate with the LASCO chronograph shown here. One is the CDAW, which is a manual rate. This is with somebody sitting down at a computer and identifying CMEs, as had been done in the previous cycles. Then people came along with a couple of automatic catalogs. They have programs that automatically identify the CMEs, track them out, get such things as speeds and latitudes and so forth. These are called SEEDS there and Cactus in purple. And you'll notice, first of all, for cycle 23, which is over there on the left, the peak, compared to cycle 24, our current cycle here on the right, you'll notice that these three ways of counting CMEs seem to line up pretty well in cycle 24 and are quite a bit higher than the sunspot number rate. That difference right there. However, you go back to the cycle 23 peak around 2000 there, you'll notice that there's quite a difference in where the peaks are. There's also a double peak, which is not unusual, both in sunspot number and CME rate, and that those peaks and maxima values vary. Now, this one's not running. There it goes. Since 2007, we've had a new set of instruments from the stereo spacecraft, which stereo is in 1 AU orbit, was launched from the Earth, and there are two satellites that precede the Earth in its orbit and lag the Earth in its orbit, called A and B, ahead and behind. They have been up there for 7 years, and they're now almost around the back of the sun, back here. But they've been observing for 7 years CMEs. Now, we're not necessarily observing the same CME now with these three instruments, LASCO at the Earth and stereos as they move away from the Earth in the 1 AU orbit. But statistically, they should be giving the same rate of CMEs. And so we've added now these values since 2007. You'll see 2006 on the left and 2014 here. So here's, again, we only go through the middle or end of 2013 with this data, partly because we do a smoothing averaging, and you need several months in advance to really get that average right. So that's one reason the last few lines there are somewhat scattered, is because the smoothing isn't quite right yet. But just to point out here, the LASCO values I showed before, the solid lines, the stereo values now from, let's see, there's two different chronographs on each of the stereo spacecraft, so that's 4 views. And there's the Core 1B there in blue is manual observer counting. The other ones are done by Cactus and Seed, so there's the automatic counting. And the stereo values are all the dashed lines. And you'll see that, again, there's a huge range here above the sunspot number in blue among all these different chronographs in terms of where the maximum is in cycle 24. So does the CME rate diverge from the sunspot number rate in cycle 24? Well, yes, sort of, but more work is needed, of course, in this complex situation. So thank you. I'll turn it over. Next speaker. How do I get out of this? Okay, thank you.
So good morning. I've been given the rather difficult task of putting this cycle in context. And as we've heard from the previous speakers, we have exquisite data covering this cycle, and some of the data cover the last cycle. But of course, the solar cycle is presumably a really old phenomenon. So the question is, are we in a typical cycle, or are we in a peculiar cycle, as many of us have often said? And I must say I'm guilty of it, though these days I think I prefer the word non-canonical to peculiar. So the signs of peculiarity were there quite early. So what's shown in this view graph are the monthly average sunspot numbers for the previous cycle, that's cycle 23, and the ones for cycle 24. And I've started counting from when we saw the beginning of the cycle. And the first thing people noticed was the rise of cycle 24 was slow, and that the cycle 24 we are at the maximum now, it's low. Now, this is sunspot number, and if you hear people who deal with sunspot numbers, they'll say that it's not a very objective measurement because it depends on who's counting and how it's being counted. So there are different sunspot indices. I personally prefer the radio flux from the corona, and that too has been much lower than that of the previous cycle. So the question is, okay, the cycle is obviously not as strong as the last one. And the thing is, the cycle started from a non-canonical minimum, as Dick said, even in the temperature. But this is, I'm afraid this doesn't show up very well on the screen. Hopefully the webcasters would see it better. These are images of the solar corona taken from the LASCO, which is on Soho. This image is the solar corona during the minimum of cycle 23. This is a canonical solar minimum corona where the corona is basically planar. You see the intensity mainly in the equatorial plane. The other image is what the solar corona was during the beginning of cycle 24, and it's definitely not what you expect. So we see the cycle started off looking strange. And we had hints of that even from solar dynamics. So Rick Bogart talked about both torsional oscillations and meridional flows. These are meridional flows again, but what has been done is plot them the way you plot torsional oscillations. So the x-axis is time, the y-axis is latitude. These are 4 different depths, so you can ignore that. You can just look at this graph. Cycle 24 minimum, the flows where these are the equator, These are the equator to the poleward flows. In cycle 20, just around the minimum of cycle 23, or just as cycle 23 was ascending, the flows were much more, they were slower than the flows at the beginning of cycle 24. So the sun started off at a different initial condition, if you wish, at the beginning of this cycle. But then, are we in really a peculiar cycle? I think that's in the eye of the beholder. So these are now smooth sunspot numbers from different cycles, and again plotted from the point where the cycle began. The black curve here is the current cycle. Cycle 22 is in orange, cycle 21 is the dashed red curve, and the blue curve is the previous cycle, cycle 23. And you see this magenta curve? That's cycle 14 in the beginning of the 20th century. Looking at this, I would say, hey, we're just repeating what we've seen before. Unfortunately, we did not then have the sort of detailed data that we have today. So peculiar, maybe not. The sun's not run like clockwork. And in terms of the corona, yes, the corona has been non-canonical. This is a digitally enhanced eclipse image from an eclipse just before the minimum that occurred before cycle 14. And this is one before cycle 24. And in both cases, the corona was what is a non-canonical, so it doesn't look like a solar minimum corona. So maybe we're not in a peculiar phase of the sun. And in fact, if you want to use the word peculiar and that the cycle is different, well, there were differences in cycle 23. So let me explain this slightly. So you've heard of helioseismology, which is the study of the sun using its oscillations. There has been one continuously running helioseismic experiment, which now has over 35 years of data, but it takes very limited data. But it's only the most global modes of the sun. It's a sort of data that Kepler is now giving for other stars. So limited, but really high precise data. And I can take those helioseismic frequencies, and we know that those helioseismic frequencies vary as a function of solar cycle. So what's shown here in the topmost plot is how the highest frequency modes varied. What we've done is we placed the 0 point at the maximum of cycle 22. The middle plot is how the medium frequency modes varied, and the lowest plot is how the low frequency modes vary. And we can see cycle 23 itself was different. So if we want to talk about peculiarities, we have to go farther back. And so the high degree modes in cycle 24, all the frequencies track both the sunspot number, which is in red, and which is in blue, and the radioflux, which is in red. But in cycle 23, that correlation seems to break down, particularly close to the maximum and later. And I can show this more dramatically if I plot the differences here against the differences here, and the differences here against the differences here. And this is it. So red points, cycle 23, black points, cycle 22, the one before that, blue points, cycle 24. So medium frequency and high frequency seem to go in lockstep. But look at the low frequency versus high frequency. Cycle 23 is completely different from 22, and 24 is going off in its own direction. So, which means that the sun is continuously changing. So to say cycle 24 is maybe just a lack of data. So this solar cycle may not be strange in the grand scheme of things. And our biggest problem is we only have good data for maybe 60 years, and the sun is a 4.5 billion-year-old star. So I think it's too early to panic about how the sun is changing. My personal view is we've seen this before, or we would have seen this before if we had the data. And for those of you who are interested in a bit of history, this is a slide I put in about how far solar data goes. And to this, I should probably add Dick's solar coronal temperature data, but that's also just about 30 years. So, well, 4.5 billion-year-old star, 400 years of not very good data, 40 years of really good data. So I think we should be studying the changes to see what the sun does, but being a bit careful about saying, oh, the sun is acting funny. The sun is probably acting the way it's acted before. We just haven't seen it. Thank you.
Thank you very much to all four of our speakers. A lot of very interesting things going on our star. We have a little bit of time for questions and answers. We'll start, as usual, with questions from journalists here in the room. If you're on the webcast and you have a question, please send your question in via the chat window. So do we have some questions from here? Okay, we'll start down in front with Clara. Please remember to identify yourself by name and affiliation.
Hi, this is Clara Moskowitz with Scientific American, and my question is for Dr. Altrock. In terms of the corona temperature, do we know much about the mechanism behind the temperature? You know, what's driving that temperature? Is it related to magnetic activity or what? Thanks.
Well, that's been a subject of a lot of debate, and I'm not really sure whether that the question of what causes the solar temperature has been totally defined. There's a number of different theories and models that try to tell how the temperature of the solar corona is created. And I guess from my point of view, I'm not really clear that any of them have been totally shown to be correct.
Okay, did anybody else want to comment on that? Okay, any other questions? Yes, over here in the back, or in the middle.
Rich Wolfson from Middlebury College. I have a question for Dr. Basu. Do we know how after 1914, how long did the peculiarity linger? Was it several cycles before things recovered, or was this a sort of one-shot anomaly?
If I remember the sunspot distribution correctly, the next cycle wasn't too high either. In fact, it's only the past 5 cycles that have been so high. And there was a whole period of low solar cycles, low amplitude solar cycles before that. So it just happens that the space age coincided with a really active sun. So.
Okay, you said there was another question over here? Oh, yeah, okay.
I was just
Can, hold on and wait for the mic. Thanks. And identify yourself.
Lika Guha Thakur, the NASA headquarters. I was just going to add to what Dick said with regard to the question about coronal heating, and waves of different sorts are sort of thought to be raising the temperature in the corona. And as Dick said, there are all kinds of theories, and observations are in situ. Observations are limited in that region. So it's been one of the outstanding problem of physics in general. And to answer that question, actually, we have a mission called Solar Pro Plus, which will actually go into the corona within 10 solar radii, measuring the particle data as well as waves to answer, to essentially verify or not verify some of the theoretical insights we have on that.
Okay, down here for Monica.
Monica Young from Sky and Telescope. This question is for Dr. Bogart. I was curious about, like you mentioned, the meridional flow is what governs, or is thought to govern the solar cycle, and I wasn't quite clear on how the east-west, the rotational flow, relates to the meridional flow. Does it mitigate it or anything like that, or are they kind of unrelated?
I don't think that they are strongly related. I think there do seem to be these jets in the east-west flow at which whose boundaries mark where solar activity, magnetic activity occurs in the lower latitudes, and they do seem to be advected towards the equator, which is actually the opposite direction of the meridional flow, but towards the pole at the high latitudes, which is in the sense of the meridional flow. The meridional flow is important because it transports the magnetic flux from these active regions that occur at the low latitudes towards the poles, where it produces a change in the net dipole field of the sun. That's how we think that the solar cycle actually occurs. It's through the transport of magnetic flux by these meridional motions. But it's not clear that the jets themselves are directly related to these meridional flows. They're just advected by them, as the magnetic field is.
Okay, we have one in the back here on the left.
Thank you. Excuse me, Maggie McKee, and I'm freelance. I was just wondering if there's any kind of overall picture of what is going on inside the sun over these long periods of time. What could be driving these different, these variations in cycles?
That's the million-dollar question in the field. So the picture, the scenario is that there's a dynamo inside the sun, which generates the magnetic field, and we think that the dynamo lies sort of at 70% of the sun's radius, so about 300 megameters below the surface. And the reason we think the dynamo can be there is because their solar rotation profile changes drastically there. So there's a big shear layer. So you can generate a dynamo by basically if you move electrical charges very fast, you can generate a dynamo, and that basically we think is what's generating the magnetic field. Those fields then become strong enough, rise to the surface, which we see as sunspots. I mean, this is the cartoon. How things happen, why things happen is still something people are studying. For one thing, why 11 years? So it's believed to be related to the speed of the meridional flow from the equator to the pole. But is it only that? What sets the speed of the meridional flow? So these are questions which we are just about able to probe now, because the last cycle was the first cycle where we could see changes in the meridional flow. We could measure the subsurface meridional flow, but we still don't know how deep the flow goes, which we hope with new data from the HMI instrument on SDO, we can do that. So these are things which is a field, this is a field of active research. Because after all, at some point, what we want to do is to be able to predict what the next cycle is going to be like, because sunspots in the next cycle, hopefully, once we know how many sunspots are there, we can, if need be, take protective measures, because strong sunspots can produce flares and CMEs, but that's the holy grail. Can we predict the next cycle? But to do that, we need to know what sets the cycle, and we're working hard. We're not there yet.
Okay, we'll take one more here from Steve.
If we can go back to 10 years ago, or at least before the last minimum, and not count any forecast after that time, if I remember correctly from the media reports and science magazines, there were predictions of the 24th sunspot cycle, peak and timing and all, at least the peak, I don't remember the rest, we're all over the map, if I'm not confused. Did anybody's prediction, whether having a valid physical base or not, come close to what we had?
Yes.
If we look at the entire range of predictions, because they went from very strong to very weak, I think I've seen one. I don't remember whose it is, but I'm pretty sure it's a fluke, because the predictions were all over the place. And the problem is, we still do not know the complete physical basis of what sets the cycle, what sets the cycle strength. And if we know that better, we're trying very hard, I think prediction would be an easier problem.
Do we have any on the webcast? Okay, we only have time for like one or two.
All right, I'll combine them then. This is from Pete Spots with the Christian Science Monitor. Where does this leave us in relation to concerns raised in 2009 about the possibility of heading into a grand minimum? Don't bet the rand? Doc? And then Elizabeth Pearson has a follow-up to that from, she's from BBC Sky at Night. Further to Pete's question, will we have to wait for the next cycle or longer to be sure?
Okay, I think we have two different answers. Okay, my answer is part of the issue of the grand minimum was an observation that the peak sunspot strengths were falling, but I believe that's no longer the case. So we may not be headed to a grand minimum. Sorry, what was the second question?
And then further to that, will we have to wait for the next cycle or longer to be sure?
My bet is it's going to be short, but that's because the meridional flows are faster. Not everybody agrees with me because we don't quite know what sets it, but Rick is probably going to have a completely different answer and Frank Hill, who's the director of NSO, may have a different answer altogether.
No, I don't think I have a completely different answer. I think the problem here is really it's a paucity of data. The stronger cycles during the mid-20th century were actually consistent with something that has been posited for a long time as the Gleisberg cycle, a super cycle that lasts about 8 or 9 solar cycles of variation in the amplitude. So we're on the declining phase of that. But when you think about the history of the data, we don't have enough measurements to have more than like 1 or 1.5 samples of a cycle, and that's not really enough to really be able to predict a periodicity. In the case of the grand minimum, we only have one instance that in the Sunspot record. It's a very poor record at that. We have no idea what was happening before that, in the cycles before that. So we really haven't I think we're pretty much clueless as to what causes a grand minimum. If I could just make a comment, I mean, whatever predictions we're going to make are going to have to be based on models of how the activity cycle occurs, and that's what we're trying to. That's why we're trying to get at this, because just basing it on historical data is going to be a very tedious process. We'll have to wait 400 or 3,000 years before we understand grand minima, probably just statistically. It's pretty clear from the work I've been doing and the work that Dick Altrock talked about that even though solar activity manifests itself at low latitudes, sunspots tend to occur between like 5 and 40 degrees in latitude, what's actually controlling the cycle and maybe the strength of the cycle and whether the cycle comes or goes at all or disappears or whether it's delayed is occurring at the high latitudes in the poles. And that's been very hard to study because of the foreshortening. The Earth is at a very low latitude. It's at only 7.25 degrees heliographic latitude, which means we don't see the poles very well. They tip very slightly towards us or away from us over the course of the year. But it's very hard to see what's going on without very high resolution. And we're only just beginning to see that with some of our high resolution instruments in space now. And I think that may make a big difference for our understanding of the structuring of the cycle in the future if we can keep studying that.
Okay.
Okay, thank you. I think I'm going to have to wrap it up here because we're running a little bit late. If our speakers are willing to stick around for a few minutes, those of you who are here in the room can come up to the table and ask your questions. I'd like to take this opportunity to thank Craig DeForest again for helping to arrange this briefing, for our 4 speakers who presented some very interesting data and some very interesting context and explanation of what's going on and how we have to treat our understanding of the behavior of the only star that we can see at this level of detail. I'd like to thank all of you for participating and just remind you that we have another press conference this afternoon at 2:15 p.m. here, Galaxies Across the Spectrum, where we'll be looking at objects much farther away than the sun at a variety of colors. So thank you all very much, and we look forward to the next briefing later today. Thank you.